Jacob is next, and his mentor, Michael Rutkowski, is here. Awesome. Would you like to introduce your intern?
I'm trying to get can you hear me?
Yes.
The video is not working too well. Oh, there we go. So I'm Michael Rutkowski. I'm at Minnesota State University, and I was privileged to supervise Jacob this summer. Jacob is actually just a little bit down the road from me in Rochester, Minnesota, and which is great because we had such a good time this summer. We'll continue working on what we did. He'll introduce what he did, of course, but he was actually, I think he's the first person ever to look at this new data that we have from the James Webb Space Telescope, a program that was obtained, or that obtained imaging and spectroscopy of high redshift galaxies. So I'll turn it over to Jacob.
I'll get my presentation up here. Notice. All right, so my project was about the imaging from the James Webb Space Telescope. So the JWST imaging and slitless spectroscopy it's been obtained for over 30 random positions as part of the PASSIVE program. So this is not targeted. The main camera is targeted. This is a side camera module that is just looking at several fields over here. So this is an example of one of them here. So this is the larger field, and from within this, it's separated into many individual images that I'll be talking about in a bit. So the goal of the project was to use the near-infrared imaging to identify and classify various galaxies, as well as searching for distinctions in the emission line properties of bridge galaxies. So I'll be telling you what those are later. It'll make a little more sense there. One of the things we looked at were the Balmer lines, which rise in the interstellar medium as signatures of star formation, and that's based around the energy levels of the hydrogen atoms that have varying numbers of electrons, and so those emissions can tell us a lot about star formations. So our idea here going into this was that if the emission line intensities of the merging galaxies are systematically higher than the general population, given the fixed ranges of redshift and stellar mass, then these strong lines could possibly indicate that the mergers enhance the recent star formation in these galaxies. So that's what a lot of the analysis has been about. And then as an addition, there are a lot of these fields to look at, and it would take a human a very long time to do so. So these images are also going to be used to train machine learning software to classify the galaxies and new fields for us so that we don't have to go through them, because it takes a lot of time. Yeah. So there's examples of different morphology types. So these are the different types of galaxies. I'll start off with these spirals that you're probably fairly familiar with. So that's where you have the bulge in the center and then the arms coming out of it, such as our own Milky Way. So that's not as common as you may expect. I actually didn't find a ton of these in the deep space imaging, but they are the most iconic shape of galaxies, I would say. So next we have spheroidal, and this kind of lumps together a lot of different types. It does include all of the elliptical galaxies, but it also includes many galaxies that wouldn't normally be classified as ellipticals due to properties, but are mainly one large clump or bulge of stars. And so it's kind of a catch-all that just gets anything that looks like a lump. So here's some examples. And then the tadpoles are a third type, though not the final type, as you'll see. And so those ones have a bulge not centered, and there's a trail of stars and gas coming out of it. So it looks kind of like a tadpole or like a comet, you would think. So that's how I get that. Yeah. A few more types that I looked at and classified. So chain galaxies here. This one's on the bottom is a really good example. So that's where you have several different clumps of stars, all kind of in a row, in a line, making sort of a chain. And so those ones are there. Then there's clump clusters, which is where you have several clumps, not in a row. They're just kind of scattered here and there, wherever, but they're still physically near each other, or at least appear to be. And so the two examples of those are here. And then there's merger galaxies, and that's where you have two of them that are physically close and could be colliding in the near future or appear to already have collided. And the bridges are, not all of them have this, most of them didn't, but if they already have collided and have passed through each other, they'll have this bridge that you can see in here where it's kind of a stream of dust and gas and stars that connects them. And so those ones have some interest, are of interest because they've already collided. So the question is, does this collision and passing through each other kind of shake stuff up and cause star formation to occur? Then there are some non-objects, and a lot of the images were not of interest. So whether it's just noise picked up by the camera or some really weird artifacts. Yeah, there's one that I really liked. This one, at first I thought it was a black hole, but that didn't make a lot of sense to me, especially with the light coming out of it. It's actually a very close star, and these pixels of the star got maxed out and just blocked by the camera so that they wouldn't damage the instrument. So this is an example of one of the PDFs that I was looking at that had the imaging here, as well as a lot of interesting data, which I'll briefly talk about. So this is the near infrared imaging at 1.15 and 1.50 microns, and then these get combined to create a color image, which gives a more accurate representation of it, because when you overlay the two of them, it accounts for any bad pixels or interference in one camera that isn't seen in the other, gets erased or diminished somewhat. So you get a much clearer view of that. Then there's the slitless spectroscopy from 1 to 1.5 microns, which this is a graph of the emissions that, the strength of the emissions at various wavelengths that are detected, and they are redshifted, of course, so it's not always going to be the same emission line for every one in a specific point. So that's where analyzing the patterns comes in a lot. Then there's the 2D overlays, so taking a kind of a graph of it, of the spectral strength, the strength of the emissions that are detected, and then also rotating it 90 degrees and taking another image at a later point and then overlaying them to get a more accurate thing, to get a more accurate image, to again reduce the effects of interference for a single photograph. And so that can be used to verify the validity of these data sets. And so the bottom one is the combined. So that's, and then finally there's this graph of the redshift probability distribution, and that's basically saying, okay, based on the emissions that we've detected at various wavelengths, where do we think, how far away do we think that this is? And then it's creating this graph so that the peaks are the most likely points here for it to be. And the redshift, if you know the redshift, you can calculate the approximate distance due to the nature of the ever-expanding universe. So how did I complete this project? I used a Google Sheets document to record all my classifications, and then once I had done all those for the first region, PAR 1, I took those and ran it through a Jupyter notebook and created some Python code to perform statistical analysis of the spectra. And so it's in this flowchart here, you can see the process for classifying any object. So you start with an object, then you figure out which morphology class it fits into best. So whether it's a non-object, it's not interesting, discard it, move on. If it is an object, I marked whether it was a possible merger or not. If it is, I marked it as being one, and also if I thought it had a bridge. And then I looked at the redshift graph, and if it was very clear, kind of like this one here, that you see where it had mainly one clear point or mainly a few clear peaks there, then I would be more confident that the given spectrum was correct. But if not, I would simply write that I couldn't really be confident about which emission lines I was seeing. So the results, I found that around 10% of the identifiable objects in par 1 were mergers, so that was pretty interesting. And between par 1 and about a third of par 5 I've also worked through, I found a total of 36 bridge galaxies, and those will be used as the start of a training set for machine learning software. And then to perform the statistical analysis, I used a KS test to calculate the possibility of a significant difference between the distributions and the strength of emission lines in mergers versus non-mergers. And there'll be some graphs here after this. So this is just some examples of what the bridge galaxies look like. So this is the one I showed earlier, but there are some others here, and you'll notice they always follow this pattern of having two main objects and then a connection of dust and gas and other stars that's a lot dimmer. But that's that bridge that's showing they've already collided, they've moved through each other, they've dragged some of each other out a little bit, and that's kind of the leftovers. So the KS test is used to calculate the probability that the two samples are derived from the same population. So for each of the 4 major emission lines I've observed, those being the hydrogen alpha, hydrogen beta, oxygen 2, and oxygen 3, lines, I performed a 2-sided KS test to see if there was a significant difference between the distributions of the emission strengths for the mergers and the non-mergers. And so what the goal of that was to see, okay, we have the data for how strong the emissions are. Can we determine if there is a significant difference? And can we figure out if this is possibly related to active star formation? Which I'll mention in a bit. So I have these graphs here of the emission line intensities. So for each pair of images, so on the left and the right, you'll see the labels underneath them. And so the left image is not restricted by redshift. The right image is restricted by redshift. And the idea behind that restricting by redshift is just to get rid of some of the noise and anything that seemed not reliable within the data sets, because there were some outliers that logically didn't make a lot of sense. So those usually had very strange apparent redshifts too. So restricting by the redshifts here just made it easier to get a more accurate sample of these. So these are all a logarithmic scale for the x, and then the y is based on proportions, not the number of observations. So that way, with the orange being the mergers and the blue being the non-mergers, the blue ones weren't all about 9 times as tall as the orange. And so you can get an accurate comparison of the distributions without worrying about having a large disparity between the heights of the graphs.
Jacob, I'm just butting in to give you like a 1 to 2 minute warning to move things along, please.
Okay.
Thanks.
This is the result of the KS tests here. So, and a bit of the Python code that I wrote. So these p-values are the probability that given no difference in the parent populations, we would see data this extreme. So in this case, with the oxygen 2, we see that it had a p-value of 0.0039 roughly. And that indicates that there may be a strong possibility that there is a significant difference in the oxygen 2 emission line strength between the distributions of those for the mergers and non-mergers. However, we didn't normalize for stellar mass, and since larger our greater mass galaxies will have stronger emissions overall, simply due to simply having more stars and more mass that is emitting these radiations. So we cannot treat these as conclusive results. We'll need to do that in the future, but it is a starting point for future research. I'm gonna skip this because I mostly mentioned all of this. So future directions, I'm going to be continuing work with Michael this semester, looking to kind of refine the population, get a better sample of the bridge galaxies, and ideally be able to normalize over the mass and redshift. We'll be starting work on some machine learning software and using that. So far, Michael's run some machine learning stuff that has been insufficient in its efforts to differentiate the bridge and non-bridge galaxies, so we'll need a larger sample for that and be improving the model. And then the classifications will be used in the spring of 2024 as part of a CS class, which will be creating those machine learning systems to analyze the remainder of the images that humans don't have to do it because it took a really long time. There were thousands of images to go through, and that's a lot. So acknowledgements, I would like to thank the Passage team led by Matthew Malkin for the chance to explore these data. They are classified, so normally I would not be able to, but I'm really appreciative for the chance to do that. Of course, thankful to the N3 program for providing me with the opportunity to work on this, and thankful that Michael has been such a great mentor and been excellent to work with on this project. And with that, does anyone have any questions?
Thanks, Jacob. Let's give Jacob a round of applause.
Yes, I'm wearing my James Webb jewelry here in honor of this project. It's so exciting that you get to work on, stuff that's so new that most people aren't even allowed to see it. It's just wonderful. And I'm so glad you're going to continue to work together. Our first and only so far intern and mentor team from Minnesota.
We'll take the one question in the chat.
Okay, how long does it take the galaxies to collide? So I don't know about that. It would probably depend on like the gravity and how far away they are and the overall size of them. Michael, do you know anything about this?
Yeah, I guess it depends on the distance they're apart, but for reference, it'll take about 3 billion more years for Andromeda to collide with us. So if you assume that other galaxies are moving at the same speed that Andromeda is moving towards us, so 300 some kilometers per second, it takes upwards of well, a kilometer per second is a parsec per mega year. So it takes many giga years for collisions at the distances of Andromeda and Milky Way. These galaxies are much, much closer. So the interactions have occurred probably within the last 100 million years, especially if we see evidence in the emission lines, because those emission lines usually go away within the first 20 to 30 million years, or maybe up to 50 million years after the star formation event. So they happened very recently on timescales of galaxies.
Well, thanks for the help. And thanks to Jacob for that great presentation.